So actually, to preface their presentation briefly, one of the things that our lab has been interested in is using fluorine NMR to look for reactive intermediates that are quite transient and challenging to characterize via other means. And so our lab has published extensively in this area. And one of the bottlenecks in this sort of research is obviously identifying a compound on the basis of its 19F NMR signature. And so this project was kind of born out of that need, which I think is now well substantiated in the literature by our group and by others. And so what we're doing is we're trying to shortcut what otherwise either would have taken weeks of experimentation or days of compute power by DFT with machine learning. So without further ado, go ahead.
Okay. Thank you. So I'm Sophia.
I'm Emma.
I'm Leia.
I'm Raina.
We'll be presenting our project on machine learning for density functional theory for 19-fluorine nuclear magnetic resonance spectroscopy.
So before we get into what our project is really about, I want to preface with an introduction to what nuclear magnetic resonance spectroscopy actually is. For those of you who aren't chemists, you're probably like, wow, NMR spectroscopy, that's a huge word. Like, I don't know what that is. So for a brief conceptual overview, NMR spectroscopy has become a very popular method in the last 5 decades to determine the atomic structure of a compound for which you don't actually know the atomic structure of. And so basically, you have a compound and you inundate it in some solvent, and you apply a magnetic field and irradiate that with radio frequency pulses, and what that will do is it'll emit a resonance back, which you can interpret as a spectra. And NMR spectroscopy is, again, very widely used. This is in part because it's a non-invasive procedure. So you can apply the magnetic field and the RF pulses as many times as you want on that compound without actually affecting the structure of the compound itself. So that's very useful. It's only used for certain isotopes, and those are fluoridated compounds, carbon, hydrogen, so like 19F, 13C, 1H, and this is because they all have 1/2 spin states. And what a spin state is well, each nucleus will have a spin state, and it's basically like a quantification of the vector of where it's turning. And when you apply that magnetic field on the fluorinated or carbonated compound, the spin states of the atoms will either align with the magnetic field, which is called B naught over here, or go against it. And these two spin states are called the alpha and the beta spin states. So the alpha spin state, which is the state in which the spinning of the nuclei is aligned with B naught, will be very significantly less energy than what the beta spin state will be, which is de-aligned with B naught. Because, well, you can kind of think of it as an analogy of swimming against a current. When you're swimming against it, obviously it takes a lot more energy, but if you're swimming with it, then it's a lot less energy. So likewise, the increase in B naught will lead to a greater delta E, the difference between the alpha and the beta spin states. And based on what delta E is, here on the bottom image, you can see that this top line, the orange one, is the alpha spin state, and then the bottom one is the beta. And yeah, delta E is just the difference between them. And so once you have the compound and the solvent, and you have it with the applied magnetic field, B naught, and you know what delta E is. So based on what delta E is, you apply a specific radio frequency pulse, and that will cause some of the nuclei that are still in the beta spin state to relax back to the alpha spin state. or to excite to the alpha spin state. And when this happens, and then they eventually, after they excite, and then you stop applying the pulse, then they'll relax back into the beta spin state, and this will release a resonance, which is where the R in NMR comes from. And this resonance can be interpreted as a voltage signal, which the spectrometer, which is the instrument of NMR spectroscopy, will show as a spectra. And from the spectra, you can glean a lot of information about the chemical environment surrounding each fluorine, which is what we're doing specifically, but also like carbon or hydrogen atoms in the compound. And here.
All right, so as Emma mentioned, NMR spectroscopy is often used to determine the atomic structure of certain compounds because it tells you a lot about the electronic environment based on signals given off by specific nuclei, which are excited. This starts with the simple fact that each nuclei has a different, distinct electronic environment. Since each nuclei's surrounding atoms and bonds vary, this means that every single nucleus has varying degrees of shielding due to each mix of atoms, specific atoms and bonds in its environment having different effects. So what exactly is shielding? Since the electrons around the nuclei within a compound is in motion, this creates an electromagnetic field. This field will then oppose the external magnetic field from the NMR spectrometer. This then means that the more surrounding electrons you have around a certain nucleus, or the higher its electron density is, the higher its shielding will be, if you can see on the picture on the left. This shielding has implications on the final resonance signal that's given off that will then be measured by the spectrometer, as the radio frequency energy given off during resonance or the induced flip state, as Emma has previously explained, will then vary. This is because, again, the more shielding a nucleus experiences, the smaller its radio frequency signal will be during resonance. And this is because of that high electron density that's around it, which will oppose the external electromagnetic field coming from the NMR spectrometer. So this means that these resonance signals are unique to each nucleus, and they will then be measured by the chemical shift values in the resulting NMR spectra, which we will talk more about in the next slide. All right, so chemical shift is a ratio relating the nuclear resonance signals and the particular spectrometer frequency being used to measure it. This means that the particular spectrometer that you're using has no big impact on the final chemical shift value that you get. And specifically, standard compounds are always used to measure the specific chemical shift value with relation to that standard compound. This is because it usually has a low frequency or a high shielding value, and they serve as a good benchmark against which all other signals will then be measured against. Chemical shift values form the x-axis of any NMR spectra, and NMR spectra can then be used to determine the structure of compounds through specific techniques, such as integration of the peaks, which can tell you how many nuclei gave rise to each signal peak, or observing the splitting within each peak, which can then tell you information about the neighboring atoms, as well as the chemical shift values that are denoted by the x-axis, which can then tell you how shielded each nucleus is. Yeah, if you just want to click through those real quick. Yeah.
So another major part of our project is density functional theory. And DFT, by definition, is a computational quantum mechanical method to describe the electronic and magnetic properties of a system. So DFT is like a shortcut to solving Schrödinger's equation for every single electron in a system. It is based off of the Hohenberg-Kohn theorems, which state that knowing the electron density of a system allows you to determine all ground state properties of a system, including total energy, which means instead of the many-body perspective, which would mean considering every electron's individual wave function, you can just consider the electron density as a whole in this DFT perspective. Next slide. So how is DFT related to NMR? Well, DFT can predict NMR chemical shifts, and it does this through the Cohen-Sham equations. So as a brief overview of how the Cohen-Sham equations work, you start off with an initial guess for electron density, or rho of R. You then use the guess density to calculate the effective potential of the system. And using that effective potential, you solve the Cohen-Sham equations for the electron density of a system. And you repeat this process in a cycle until self-consistency is reached. And self-consistency is reached when that initial guess density matches the final calculated density as given by that effective potential. And once self-consistency is reached, the cycle ends and the calculation converges. The output of this convergence would be the final density functional as well as the energies of each orbital. So DFT is able to predict the local electron density and NMR chemical shifts, reflect the local electron density of a nucleus via shielding, as Leah explained. Therefore, DFT can be used to predict NMR shifts by analyzing the local electronic environment around key nuclei, such as fluorine. Okay, so DFT is relatively accurate and somewhat efficient, but well, for context, one DFT calculation can take up to several thousands of seconds, whereas one machine learning prediction might take only a couple milliseconds. So the first major phase of our project, which we are currently working on, is to shortcut DFT using machine learning. The first subphase of this major part of our project would be to perform a comparative analysis. We'll be comparing the performances of different machine learning models on how well they can predict DFT results. And the input for these machine learning models will be the local atoms around each fluorine. We can call these atoms, well, neighbors. So the next subphase of this major project part would be asking the question, well, what is the optimal distance from which to take neighbors? How much of the fluorine's local environment do we want to know? The next future phases of our project would be, first of all, considering the fact that default density functional theory calculations, which we are using right now, are on gas phase NMR, but in experimental settings, NMR is more often performed on a compound in some sort of solvent phase, which is modeled computationally by the CPCM solvation model. So our second major phase would be attempting to shortcut CPCM solvent effects and predict them using machine learning. Another future phase of our project would be considering that DFT is an approximation of NMR chemical shifts. So we would attempt to use machine learning to predict experimental NMR chemical shifts instead. All right, so let's jump right into our methodology. We start off with data collection. Our data, at its essence, comes from ASDRP's chem inventory. We extracted 501 fluorinated compounds by their SMILE strings, or one-dimensional representations. We then converted these 1D representations into initially optimized 3D representations using OpenBabel's Monte Carlo conformer search method with molecular mechanics. After we have an initially optimized 3D structure, we further optimize it using ORCA. And ORCA is a software that is used to perform density functional theory calculations. So using ORCA, we end up with geometry optimized 3D structures. Back a slide. And we then use these 3D structures to calculate the chemical shifts, or the 19F chemical shifts of each fluorinated compound, again using ORCA's DFT calculations. All right, so after our initial data collection, we end up with a bunch of 3D structures as represented by their 3D coordinates. But the 3D coordinates themselves aren't actually correlated with the fluorine chemical shifts. After all, you can rotate a compound and the coordinates all change, but it is still the same compound. So what we really care about is the local environment around each fluorine atom. And we keep track of this local environment by running a distance formula with each fluorine atom as the root, and then we calculate the distance from every other atom to that local fluorine atom. And if another atom is less than or equal to 3 angstroms away from a fluorine, we consider it close enough to be a neighbor. And for each neighbor, we add some additional features, such as the neighbor's atomic number, charge, electronegativity, and mass number. And the result of our data processing is a data set where each fluorine can be considered an item, the input features as the fluorine's neighbors along with their own features, and the target values, which our models are predicting on, as the NMR chemical shifts.
So as for the models that we will be training on NMR data, we are working on 11 models at the moment, and we're going to start off with the multi-layer perceptron regressor. It is an artificial neural network algorithm, and it basically has many different layers of nodes, like neurons, that will predict individual values, and at the end, it'll give you one final continuous values. It'll give you one final value to predict. Next, we have random forest regression, which is an ensemble learning method that is actually based off of a simpler method, machine learning method called decision trees. And so random forest regression basically combines multiple decision trees to improve the predicted performance of the model, and it's really high in accuracy for us at the moment. And then we have support vector regression, which is a model that is based off of a support vector machine algorithm. And at the moment, we don't have a super high accuracy for this one, but we are working on it at the moment. So next one. So we have Gaussian process regression, and basically it is a non-parametric regression model, which basically means that it's not limited to the amount of parameters, and therefore it's really flexible. So basically it uses random variable collection and joint Gaussian distribution. You can see on the graph that it has mounted to a main continuous with continuous like regression, it has amounted to a main value that it will use for the prediction of the NMR shift. And then we have AdaBoost. It is also an ensemble learning method, and it uses weak learners. So weak learners are simpler machine learning algorithms. And for example, it could be a decision tree, which is not as complex as the AdaBoost machine learning itself. And basically, AdaBoost combines all the simpler machine learning models predictions, and it uses their predictions to create an even stronger average of those. And then we have bagging regression. It is also an ensemble learning algorithm, and it also trains on multiple models, and it combines their data, and it will use subsets of the data and average the different predictions for each of those models. So the next slide. And then we have k-neighbors regression. So this is a instance-based and non-parametric supervised learning algorithm, and it's really high in accuracy most of the time because it does not assume any specific underlying probability distribution for the data, and that's why we preferred to use this specific model. And then we have extra trees, which are based off of decision trees models. And basically, to start, decision trees are basically supervised learning algorithms, and they're used both for classification and regression, which is what we're doing at the moment. And they use root nodes, internal nodes, and leaf nodes to come to predictions. Because these are not the most complex, best performing models themselves, there's extra trees, which are based off of decision trees. And extra tree algorithms basically build off of the multiple decision trees, and the difference between extra trees and random forest is that extra trees actually use the entire data set to train. Then we also have ElasticNet, and this is our only linear regression model at the moment, but it is great for multicollinearity, and it is also great for overfitting predictions in which it is not entirely very accurate in the predictions for the shifts. So all the models I listed so far all use similar data processing techniques. So we basically have 2 more models that have different data processing techniques that we haven't gotten to yet. and we are working on them at the moment. And these two are called graph attention neural network and graph convolutional neural network. And basically, the graph attention neural network is trained on graph structured data, and it uses feature vectors. And this is also very similar to graph convolution network. And it basically is based off of nodes and edges, and it is also trained on graph structured data. Those are all the models we have at the moment.
Yeah, thank you. So for our results, we created a bar graph showcasing all the different models as well as the MAE and R squared for that. I want to emphasize that these are our initial results before any fine tuning. So while we do have all the most recent features in this graph, these results are definitely not going to be representative of like the best case of our models. And so for those of you who aren't familiar with what machine learning is, MAE and R squared are very common evaluation metrics to determine how accurate a model is. And for MAE, which is mean absolute error, basically it takes the outputs of the model and it compares it to the ground truth, like the training and testing data y values. So yeah, it does what its name is, finds the mean absolute error between the ground truth values and the model's outputs. So we want, ideally we want a very low MAE of 3 and below ppm. Currently we're generating values of like 4 to 14, but that is to be expected as we haven't fine-tuned yet. Comparatively, our R squareds are doing fairly well so far. And if you guys are familiar with linear regression, then you know that R squared, when it's greater than 1, that means that the line of best fit that is produced by the model is close to all the data points. And then an R squared that's very close to 0 would mean that there is little to no correlation between the line of best fit and the data points. So what we're looking for is a very high R squared and a very low MAE. Currently, random forest, decision tree, BR, and GBR are doing the best so far, with ADB and a very high MAE of almost 15, and GPR doing the worst. Right now, we don't have concrete reasoning behind why certain models are doing better than others, but that is something that we're working towards in the future.
It's the difference, Emma, between true value and predicted value.
Yeah, thank you.
Sure.
So our next steps would be running our analysis on from what is the optimal distance to take the neighboring atoms for each fluorine. So we currently have preliminary results comparing the performances of our models on 2 versus 3, 4, and 5 angstroms, as well as their runtimes. So we are trying to achieve a balance between efficiency and final performance. So just based on these results alone, it seems that around 3 angstroms is the optimal distance, as the 3 angstroms results achieve a relatively low MAE, relatively high R squared, and a moderate, reasonable runtime.
So currently, fluorine is one of the most popular organic elements used in synthesizing organic compounds and pharmaceutical drugs due to some of its specific properties, as outlined on the upper right diagram. For example, its high electronegativity can increase overall molecule stability. And for some context, 12 out of the 55 drugs approved by the FDA within the past year of 2023 were all fluorinated, which is around 20 to 21%. The two diagrams in the lower right corner show some of these specific compounds that were approved for the years 2020 and 2021, just to give some context. This growing interest in fluorinated compounds makes our machine learning alternative to traditional DFT calculations incredibly relevant in this day and age, especially for experimental chemists working in the lab looking for a way to validate their guesses. Our machine learning alternative will provide a much less computationally intensive alternative when deducing compound structure. This will serve to also increase accessibility to a wider range of labs and individual researchers who have varying degrees of computational power available at their disposal, making structure determination much easier for scientists all across the globe.
So we would like to thank Dr. Njoo and the members of her group, as well as ASDRP, and thank you for listening. Do we have any questions?